Hello! In the previous video, we learned that Albert Einstein made the suggestion that to explain photoelectric effect, maybe we should consider whether the light is actually not a wave, but a stream of energy balls called photons. So you may be wondering, what difference does it make whether the light is a wave or a stream of photons? Well, the difference is in the way energy is delivered to the electrons trapped in a metal lattice. If light is a wave, then the energy will be transferred in a continuous manner and also in a distributed manner, in a sense that the energy will be shared by all these electrons. But if light is a stream of photons, then the interaction has a totally different feel. So you see this photon here? If it hits an electron, the electron absorbs the energy of the photon, it escapes. So it's a one photon, one electron interaction. One photon, one electron. It's kind of like the liberation of this electron has nothing to do with the other electrons. All these electrons are just hoping that they'll be the lucky ones to be hit by a photon so that they can absorb the energy and escape. Now let's figure out how the Ke of the liberated photoelectron is related to the energy of the photon. So this diagram here shows the energy levels in a metal lattice. 0 electron volt always represents freedom. If an electron wants to escape from the matter, you must make sure you have 0 electron volt of energy. Because if you are trapped in the metal lattice, it means that you are having negative energies. So this represents all the energy levels where the valence electrons in the metal lattice sit. Now let's suppose we have one electron which is currently having an energy of negative 5.8 electron volts, and say it's so lucky that it gets hit by this photon which contains 7 electron volts of energy. So the electron absorbs these 7 electron volts of energy and escapes with a Ke of 1.2 electron volt. Get it? It requires 5.8 electron volts of energy to escape. So when the photon provides 7 electron volts, it uses up 5.8 electron volts to escape, and the balance of 1.2 electron volts is the Ke of the photoelectron. Say there's another electron currently having this energy, negative 5.0 electron volt. So this guy is less trapped compared to this guy. Perhaps it's nearer the surface of the matter. Now if this electron is also hit by a 7 electron volts photon, it's going to escape with 2 electron volts of energy. How did I get 2? Well, 7 minus 5 equals to 2 electron volts. Now the least tightly bound electron in a metal lattice will be sitting here, and let's say it has an energy of negative 4.1 electron volts. So when this electron is hit by a 7 electron volts photon, it can be liberated with a Ke of 2.9 electron volt, because 7 minus 4.1 is 2.9. Now notice I say that this is the maximum Ke. So we are having the scenario where the piece of matter is being illuminated with a monochromatic light such that all the photons have the same energy, 7 electron volts. But despite all the photons having the same energy, the liberated photoelectrons have a range of Ke. But among them, Ke max will come from those electrons which were previously least tightly bound to the matter. Now this minimum gap between being trapped in the matter and freedom is called the work function. So what is the relationship between Ke max and the work function? So let's look at this equation here. This equation is saying that Ke of the liberated photoelectron is equals to the energy of the photon which it absorbed minus away the work it must do in order to escape from the metal lattice. Now since some electrons in the metal lattice are bound more tightly than others, so there's a range of the required work done, and therefore there's also a range in the Ke of the liberated photoelectrons. But Ke max must be given by Hf minus the work function, because the work function represents the least amount of work that must be done for the least tightly bound electron to be liberated. So this equation here is called the photoelectric equation. It's a very important equation, so keep this equation in mind. Okay, now we are going to relook all these contradictions and see whether the photon model of light is able to explain all this. Let's remind ourselves what our predictions were regarding if we change the intensity of the light used. So according to the wave model, if we use a brighter beam of light, we predict that both the rate of emission and the Ke max will increase. The reason we believe the Ke max will increase with intensity of the light is somewhat similar to the process of evaporation. If this pot of water is at a higher temperature, let's say we compare 30 degrees Celsius water and 90 degrees Celsius water. The 90 degrees Celsius water should be evaporating at a higher rate, and not only that, those water molecules that manage to escape should also escape with a higher Ke. Now what if light is a stream of photons? Then our predictions should be something like this. So if the light beam is more intense, what it means is more number of photons arriving per unit time. So if more photons are arriving per unit time, then the number of photons being liberated per unit time should also increase. So just like the wave model, the photon model also predicts that increasing the intensity should increase the rate of emission. However, the photon model will predict that the Ke max remains unchanged. Do you see? Even though we have more photoelectrons emitted per unit time, they do not travel at the highest. Why is that so? Because we believe that Ke max is hf minus work function. So let's say our matter has a work function of 4.1 electron volt. And let's say we are using light which contain photons of 5 electron volts. So the Ke max should be 0.9 electron volt. If more photons are arriving per unit time, then more photoelectrons will be liberated per unit time. But you will not be getting any photoelectron with Ke higher than 0.9 electron volt, because every electron can only absorb one photon before it escapes. Now some students are going to ask, why can't the electron absorb 2 photons? That's a very good question. So it turns out the probability of one particular electron to be hit by a photon is actually very low. It's like striking Toto. So the chance of an electron being hit by 2 photons at the same time is practically zero. So what must we do if we want to produce photoelectrons with higher Ke? Now, unless you are going to change the work function of the matter, if not, the only thing you can tweak is the energy of the photon. So we need photons which pack more energy, maybe 7 electron volts. Only in that case, you can get a higher Ke max of 2.9 electron volts. So do you see the photon model predicts exactly what was observed? If we increase the intensity of the light, we get a higher saturation current, because more photons arriving per unit time means more photoelectrons being liberated per unit time. But the stopping potential remains unchanged because every photoelectron absorbed the energy of one single photon. If you don't change the energy of the photon, you cannot change Ke max. What does changing the energy of the photon mean? It means using light of a different frequency or wavelength. So if you switch to another light beam that has a shorter wavelength or higher frequency, then you can knock out photoelectrons at higher Ke max, which means higher stopping potential. Okay, what about the thing about threshold frequency? Let's suppose we are doing photoelectric effects on a piece of matter that has this amount of work function. And let's say the lights we are using has photons whose energy is hf, less than the work function. So in this case, no photoelectron will be emitted. Again, it's because an electron can only absorb the energy of one photon. The chance of an electron being hit by 2 photons at the same time is practically zero. Also, if this electron were to absorb the energy of one photon and therefore has this amount of energy now, it starts from here, it absorbs the energy hf, and now it has this amount of energy. It will immediately lose this energy and fall back here. There's something about these electrons which are not very good at holding extra energy. So that rules out the possibility of electron accumulating the energy of few photons before it escapes. So if the energy of a photon is not enough, then having more arriving per unit time doesn't help, because this electron must be liberated in one energy transaction. Absorb one photon and leave. If the energy of that photon is not sufficient, then it have to remain inside the piece of matter. In fact, now we know how the threshold frequency is related to the work function. The work function must be equals to hf naught. F naught is the threshold frequency, because every photon must pack at least this amount of energy in order for any electron to be liberated. Again, this agrees with observations that if the light has a frequency that's below a certain threshold frequency, then photoelectric effect is not observed. So the photon model is doing really well so far, right? So there's just one more thing, the thing about having no time delay. Let's remind ourselves why we thought that there ought to be a time delay. That's because we were thinking that light is a wave that transfers energy continuously to be shared by all these electrons. So it takes time for all these electrons to accumulate the energy until they are energetic enough to be liberated. But if light is photon, then it's a different story, right? Because the moment the photon arrives, the electron can escape, provided the photon has enough energy. So it's this one photon to one electron interaction that explains why there is no time delay at all. Because the liberation of individual electrons is immediate. So it looks like Albert Einstein is right, because once we consider light as consisting of stream of photons, then all these contradictions are not contradictions. They are exactly what the photon model predicts. Get it? Alright, ta-ta!